Out the total internal reflection and the subtopic of chapter ray optics and optical instrument. Hmm. The total internal reflection when light travels from an optical denser medium to a rare medium at the interface, it is partly reflected back into the same medium and partly reflected to the second medium. This reflection is called the internal reflection. When a ray of light enters from a denser medium to a rare medium, the incident ray AO1 is partially reflected O1C and partially transmitted O1B are reflected. Okay. The angle of reflection are being larger than the angle of incidence I as the angle of the incidence increase, so does the angle of, and this is the figure in which we are talking about. Okay, this is the figure. So till for the ray O AO3 AO3 O3, this one. Okay, the angle of the reflection is pi upon 2. The refracted ray is bent so much away from the normal that it grazes the surface at the interface between two media. This is shown by the ray AO3. AO3. Okay. In figure 9.11, this is the figure. If the angle of the incident is increased still further, example, ray AO4, AO4. Okay, this is the AO1, AO2, AO3, AO4. Okay, reflection is not possible and the incident ray is totally reflected. This is called the total internal reflection. What we call as total internal reflection. Okay, when light gets reflected by surface, normally some fraction of it gets transmitted. The reflected ray, therefore, is always intense than the incident ray. Howsoever, a smooth the reflecting surface may be in total internal reflection. On the other hand, no transmission of light takes place. Okay, so next one is the angle of incidence corresponding to an angle of the refraction 90 degree. Okay, say angle AO3N. AO3N. This is the N. AO3N. Okay, so next one is called the critical angle. This is called the critical angle, and we write IC for the given pair of media. We see from Snell's law. Okay, we have seen in the last pages in the study class. The next one is if the relative refractive index of the refractive medium is less than 1, then since the maximum value of sin r is unity, there is an upper limit to the value of the sin r for which the law can be satisfied, that is I is equal to IC, such that sin IC is equal to n to 1. For values of I larger than IC, Snell's law of refraction cannot be satisfied, and hence no refraction is possible. So the refractive index of denser medium 1 with respect to the rare medium 2 will be n12 is equal to 1 upon 2, sorry, 1 upon sine IC. Some typical critical angles are listed in the figure. So we can see that in water 1.33 refractive index and critical angle is 48.75, and crown glass 1.52 refractive index and the critical angle is 41.14. So dense flint glass 1.62 and critical angle is 37.31. So next one, diamond refractive index is 2.42 and the critical angle will be 24.41. Okay. So next one we will continue. Okay, the demonstration for the total internal surface, so reflection. Now, all optical phenomena can be demonstrated very easily with the use of the laser torch of pointer. In it, add a few drops of milk or any other suspension of water and stir so that water becomes a little turbid. Take a laser pointer and shine its beam through the turbid water. You will be find the path of the beam inside the water shines brightly. So next one will equal to, sorry, will sense the beam from below the beaker such that it strike at the upper water surface at the other end. Do you find that it undergoes partial reflection, which is seen as a spot on the table, and below the partial refraction, hence sorry becomes which becomes out of the air and seen as a spot on the roof. Okay, 12 uh, 9.212b. So this is the figure and we are talking about one by one A, B and C. Okay. So next one we will continue. Now direct the laser beam from one side of the beaker such that it strikes the upper surface of the water more obliquely. 9.12b. This is the B. Okay, adjust the direction of the laser beam until you find the angle for which the refraction above the water surface is totally absent and the beam is totally reflected back to water. This is total internal reflection at its simplest. Okay, in this way. So next one is pour this water into a long test tube and shine the laser light from top as shown in figure 9.12c. This is the 12c. Okay. So next one, adjust the direction of the laser beam such that it is a totally internally reflected every time it strikes and walls of the tube. This is similar to what happens in optical fibers. Okay. Take care not to not to look sorry to look into the laser beam directly and not to point it at anybody's face. Now we will see the next one is prism. Okay, prism prism designed to bend light by 90 degree or by 180 degree make use of total internal reflection in figure 9.13. This is the figure 9.13 given in the these three figures are we are considering. So okay, so prism designed to be bend light by 90 degree by 180 degree make use of the total internal reflection. Okay, in figure 1 and A and B, this is the figure. Okay, the next one is such a prism is also used to invert images without changing their size. 9C. This is the 9C, and we are considering this is the figure. Okay, in the first two cases, first and second cases, okay, the critical angle of the for the material of the prism must be lesser than 45 degree. We see from table 9.1, we have seen the figure table, and this is the table we have seen. Okay, in this this is to both crown glass and dense finite, sorry, flint glass. So second one is optical fibers. Nowadays, optical fiber are extensively used for transmitting audio and video signals through long distances. Optical fibers to make use of the phenomena of the total internal reflection. Optical fibers are fabricated with the high quality composite glass quartz fibers. Each fiber consists of core and cladding. The refractive index of the material of the core is higher than that of the cladding. Okay. When a signal in the form of the light is directed at one end of the fiber is at a suitable signal. Okay, it undergoes repeated uh, total internal reflection along the length of the fiber and finally comes out at the other end. Okay, in figure 4.14, we will see the next page. Okay, in few seconds. Since all undergoes total internal reflection at each stage, there is no there is no appreciable loss in the intensity of the light signal. Optical fibers are fabricated such that light reflected at one end of the inner surface strikes the other at the signal larger than the critical signal. Even if the fiber is bent, light can easily travel along the length. Thus, an optical fiber can be used to act as an optical pipe. Okay, so next one is a bundle of optical fiber can be put into several uses. Optical fiber are extensively used for transmitting and receiving. And this is the figure for 9.14. Okay, critical signals which are converted to light by suitable transducers. Obviously, optical fibers can be used for transmission of optical signals. For example, these are used as a light pipe to facilitate usual visual examination of internal organs like esophagus, stomach, and intestines. You might have seen a commonly available decorative lamps with fine plastic fibers with their free ends forming a fountain-like structure. The other end of the fibers is fixed over an electric lamp. When the lamp is switched off, the light travels from the bottom of each fiber and appears at the top of the free and as end as the dot of light. The fiber is such decorative lamps are optical fiber. The main requirement is in fabricating optical fiber is that there should be very little absorption of light as it travels for long distances inside them. This has been achieved by purification and a special preparation of materials such as quartz in silica glass fibers. It is possible to transmit more than 95% of the light over the fiber length of the 1 kilometer. Okay, now you can expect bottom of the ordinary windows glass 1 kilometer thick. Okay, so thank you for watching.